Can you guys hear me? Good? Okay. So we're about to get started. Yeah. What do you mean?
Here's the review. Are you going to make a review?
It's already posted online.
Okay.
It's on the WordPress site for Student Union. Dr. Ditson posted it on Web Courses.
Okay.
Yeah.
Okay. It's on that.
Yeah. All right. Again? Okay. Cool. So you guys know I always start my reviews with a chemistry joke. You're gonna miss them. They're bad, but you're gonna miss them. So why was the mole of oxygen molecule excited when he left the singles bar? Because he got Avogadro's number. Okay, that was bad. You don't have to clap. I know they're bad. All right. So we're here for Chem 1 final review with Dr. Ditson. Just a little disclaimer. Some of this content was taken from like previous SI leaders, so make sure you don't only study from this, but like focus on your textbook, the ACS review book, and like your slides and everything that's pertaining that you have for your class. Okay, let's get started. Oh, it's also only going to cover like Chem 1B. There's a little bit of stoichiometry that it's helpful for like the Chem 1A stuff, but make sure to review that as well. All right. So I made the guide in order of how we cover them, not in order of the chapters, so gas is still like the last chapter. So we started with like energy chapter and like wavelength and speed of light and frequency. So there are some equations that you have to for sure know. The constants are going to be given to you, like Planck's constant is going to be given to you. But this one for sure you have to know it relates energy to Planck's constant and frequency. And we know that frequency is equal to the speed of light. Can you guys see? To the speed of light over wavelength. Also important is the Broyles equation. I probably said that wrong. And it relates the Planck's constant over the mass in kilograms times the velocity of the particle. So make sure you know these three. It doesn't include all of them, but those are like the main ones for the chapter. Okay, so we get into electromagnetic radiation. We know that the speed of light is, I don't know why there's a negative there, 3.00 times 10 to the 8th. And we know that our frequency is the number of waves that pass a point during a certain point of time. And if we increase frequency, we decrease wavelength, because they have an inversely proportional relationship. So we know that frequency is equal to the speed of light over wavelength. So if we increase wavelength, we decrease frequency. You guys got that? Okay. This is important for like conceptual questions. They may ask, if you double one, what happens to the other one? If you half one, what happens to the other one, and so on. Our visible light spectrum can be like summarized into Roy G Vib, which stands for like each of the colors. So if you can, as you can see, like we go from red to orange to yellow to green to blue to indigo to violet. And so our lowest, our waves with the lowest frequency are radio waves, and the highest frequency are X-rays and cosmic rays and so on. So the most important part of this is like understanding the relationship. That's it. All right. So if we apply it, it says an energy of 2.0 times 10 to the 2 kilojoules per mole is required to cause a cesium atom on a metal surface to lose an electron. Calculate the longest possible wavelength of light in nanometers that can ionize a cesium atom. Oh, another thing I forgot to mention. So frequency goes along with energy, so with higher frequency you have more energy. Remember that. All right, so for this, they gave us the energy of a mole, but they're asking for a wavelength for an atom. So we need to convert that. for these problems, all that you need is given. So make sure, I always start by like writing what they give me. In this case, they only gave us kilojoules per mole. And we know we want to change it to joules per atom. So the way we do that is, oh, yes, sorry. So we have that 1 kilojoules is 1,000 joules. So that way we get joules instead of kilojoules. And then 1 mole, this is where Avogadro's number comes into play, not just for our joke. So we know that every mole has 6.022 times 10 to the 23 atoms. So we solve for that and we get, let's see what I got. So I got 3.32 times 10 to the negative 19 joules per atom. So this would be equivalent to energy of the photon, or the atom. So we know from our formula that energy is equal to the Planck's constant times nu, which is equal to E and we're looking for wavelength. So if we isolate wavelength, we have that wavelength is equal to h times c over e. If we solve for that, we get 6.626. Times the speed of light, which, I mean, you can like round it up or leave it as the usual, over our energy, which we found to be 3.32 times 10 to the negative joules per atom. And so, I don't know if you guys can see that. So our final wavelength is 6.0 times 10 to the negative 7, which is equal to 600 nanometers. So that's the longest possible wavelength that can ionize the atom. Yes. Yes. So H stands for the Planck's constant. It's right here on this like little box. Yeah. It's gonna be given. So. Okay. You guys have any questions? Yeah. So again, I know like sometimes when we like see problems like this, we get scared because it's too long and we don't know what they're asking us. Start step by step. Yeah. Yes. So it's on the WordPress site for Student Union, and Dr. Ditson uploaded that information on your web courses. It's on web courses. Dr. Ditson uploaded it. Yeah. I think you can also Google Student Union WordPress site. Yeah. All right. Do you have any questions? This one? So I multiply the Planck's constant times the ratio of the speed of light over the energy that we found. Yeah. Yeah. So we got it in meters because we know like our our wavelength in the inside of that formula is going to be in meters. So make sure you know that you have to convert it to nanometers if they're asking for that. Yeah. Same backwards. So if you're gonna plug it into the equation, make sure you convert from nanometers to meters. Yeah. Okay. Can I, or no? Can I keep going? Okay. So we get into quantum numbers. And we know that we have 4 sets of numbers, quantum numbers. I actually missed one here. We're missing the ms. So n refers to our energy level. And I had more info on this. It says the energy of an electron depends on n. And so as n increases, the size, energy, and electron capacity also increase. All right. Then we have L, which tells us the shape of our orbital. So orbital shape. And we know we can find that by n minus 1. And that stands for the angular momentum. ML is the magnetic quantum number. And we find it by the negatives and the positives of the L number. Yeah, so this is orbital orientation, and ms is our spin. So it's either positive 1/2 or negative 1/2. And so we see here that our energy level number 1 can only have an S subshell because L is n minus 1. And so our ML is going to be 0, and it can only hold up to a maximum of 2 electrons. For the second energy level, we can have 0 and 1, and we can have then subshells S and P. So this one varies on L, and L varies on N. Yeah, yeah, yeah. All right. And remember that we have the diagram, how the energy levels move up. So N1, and so on. So it gets to infinity, and our energy levels are increasing. And make sure you know that if you're moving from a lower to a higher, you're absorbing energy. If you're going from a higher to a lower, you're emitting energy. Okay? So I would make sure I understand the why of this table. And as you solve problems today and like early tomorrow, I would like look back at this and make sure I understood why. So I put up a set of like problems, like options here that we have to like figure out if they're valid or not valid and why. So in this case, n equals 3, L equals 2, which is fine because n minus 1 is L. And then it says that ML equals minus 3. Now, this is invalid because our ML values have to be equal to -2, -1, 0, 1, and 2. We cannot have minus 3. For the next one, we have energy level 2. L is 1, ML is +1. That one's valid. For the next one, N equals 6, L equals 5, ML equals -3. That's fine. because everything checks out. And then n equals 4, L equals 4, that's wrong, because, so invalid. Because our mass L value is 3. Oh, another thing you guys should know, so our L's tell us, the L value, L quantum number tells us the shape of the orbital. So if L equals 0, we have an s orbital. If L equals 1, we have a p orbital. If L equals 2, we have a d orbital. And if L equals 3, we have an f orbital. So each orbital holds a mass of 2 electrons. But keep in mind that we have different numbers of orbitals. So let me show you this graph. Sorry, I didn't ask. Can I move? Yeah, okay. So keep in mind that we only have one s orbital. We have 3 p orbitals. We have 5 d orbitals. And we have 7 f orbitals. And if we know that each one of them can hold 2 electrons, the mass we can have in an s orbital is 2. Here we have 6. This one, like all the d orbitals hold 10 electrons, like overall, and f orbitals hold a mass of 14 electrons. So this is key, like super important to be able to do electron configurations for atoms and ions. So make sure you understand this. And we'll go into that in a second. So with that, we have a few rules that are also key. So in order to fill these orbitals, we have to follow these like main 3 rules. So electrons occupy the lowest energy orbital available, so 1s before 2s, and they fill in that order. I'm going to show you how to do it with a periodic table, which I think it's easier, but if you do like the rain method, then that's up to you. We have the Pauli exclusion principle, which says that no 2 electrons in an atom can have the same 4 quantum numbers. So for example, if we have 2 electrons in the 1s orbital, even though that their n is 1, their L is 0, and their ML equals 0, their MS is different. So one of them has a plus 1/2, which is like that one, and then the other one has a minus 1/2, which is that one. All right. Hund's rule: when filling degenerate orbitals, electrons fill them singly first with parallel spins. So if we have, let's say, p orbitals, let's say 4p, we have to fill them each like that before we can start pairing them up. Okay. So an off-ball just says that we have to fill lower energy levels first to be able to move forward, like to be able to move up. So we cannot have 2s before 1s and so on. Yeah. Any question? Good? All right. So another thing that's important, like for electron configuration, is being able to distinguish the valence electrons from core electrons. So valence electrons, let's see, the exact definition. So valence electrons are the electrons in shell with highest energy level. So our outermost electrons. And there's different different rules for for finding the valence electrons from the main group elements and the transition elements. So for the main group elements, you have to know, so our main groups are 1 and 2, and then so S block and P block. You have to know that their valence electrons are the NS and the NP. For transition, though, we have that the valence electrons are NS and N-1D. Another thing, so to keep in mind is that our the electrons from the s orbital are the ones that get filled up first, and that's true when we're making ions too. So we remove electrons from the s orbital first as well. Yeah. So keep that in mind, because they may ask you to identify the electron configuration for an ion in the transition element. So you have to know that the s orbital gets emptied first, then the d orbitals. Yeah. Sure, if I find. Hold on. How about I turn this on? Higher.
Higher?
Yeah.
I don't know. Just stand here.
Really?
Hopefully. Or
I'll hold it, it's fine. Can you guys? Ooh. Okay. All right. All right. So, do you guys want me to recap this, or should I keep going? Okay. So we have our S block, our D block, our P block, and the F block. We usually don't get to this far, but knowing them helps, I guess. So we have to determine the number of valence electrons in each element. So first, the periodic table is your best friend. So if we look at our periodic table, we find that barium is here. So our valence electrons is 2. For cesium is on the first group, so that's 1. Nickel is here in the transition elements. So we know that our valence electrons are going to be S plus N-1D. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then for our sulfur element, it's going to be NS and NP. So 1, 2, 3, 4, 5, 6. Does that make sense? Yeah. So Ni, thank you, that's a good question. So Ni is part of the transition block. Let me move this. So it's part of the transition block. And so we know that valence electrons there are NS and N-1D. So in this case, nickel is on the 4th period, so our NS is going to be 4s2, and then 3D, 1, 2, 3, 4, 5, 6, 7, 8. So if you add them together, it's 8 plus 2 gives you 10. Does that make sense? Yeah. So when you're taking them out, you also take them out from the s orbital first. I think I have a problem with a transition element coming up. Okay, does everyone get that? All right. So remember that our valence electrons are the ones that participate in reactions. So those are the ones that we remove or we add electrons to them. So electron configuration, writing all energy levels that are filled with electrons and how many in each. So we have a long way and a short way. For the long way, we just go throughout our blocks. So we know that S can have a maximum of 2, And then we move into, like, depending on the block. So for these first 3 rows, we write like each energy level S and then P, and then we move on to the orbitals. So there's a shorthand where so I'm going to write both of them. For lithium, so lithium is atom number 3, element number 3. So the longhand, I know there's not like a big difference because it's like, it's right there. So it's 1s, 2s1. But the shorthand will be the equivalent of taking the noble gas prior to that, which is helium, in brackets, and then the energy level corresponding to that period. You see? Yeah. You should be able to solve and understand and write both of them. Yeah. Yeah. Oh, sorry. Yes, 2s1. Thank you, Skyen. So 2s1. Because it's on the first group. All right. So now we move on to so for example, this question has them like all long configurations, so you should be able to like recognize both of them. So selenium, we have to find where that's at. So we find that selenium is on the nonmetal side, energy level 4, and so we're going to have S, D, and P orbitals there. So if we were to write the shorthand, hold on, can you guys hear me from there? Yeah. Okay. All right. So for selenium, if we write, I'll just hold it. For selenium, we have it there. So if we were to write it shorthand, we would see that argon is the noble gas before that. So argon, and then since it's in the period 4, 4s2, 3d10, because we get them filled up, and then 4p, and we count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our p is 1, 2, 3, 4. P4. So if we were to do it longhand, this is going to take a little longer. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. Okay, do you guys see that? You just go like by the row and understand like how many electrons can it hold. That's it. Yeah, right. So the one that matches with that is it's B. So this one. All right. All right. Yeah. So yeah, we do have exceptions, especially in the transition element. So copper, let's see. I believe this column is, well, maybe not all the way down. Well, like, at least copper and silver are exceptions because we have added stability. So in that case, we fill the orbital completely and leave like the 4s with less electrons. So I would look back and see like why there are exceptions so that you can like visualize it. It's because of added stability to the atom itself. Yeah. All right. So, where were we? All right. All right. So what is the electron configuration for the iron ion, and indicate whether it's paramagnetic or diamagnetic? So let's review these concepts really quickly. So we know that paramagnetic attracted to magnets, and diamagnetic are not attracted to magnets. And the condition for that is that paramagnetic, we have unpaired electrons. So, I don't know where to write that. So, electrons are not paired. Oops. Okay. Thank you. Well, why? Holly. It turned off. I don't know why. Like the screen. Look. Oh, that's it?
I think so.
Oh, thank you. Back on it. Sorry, guys. I don't know what's happening today. All right. So electrons are not paired for paramagnetic, but they are paired for diamagnetic. The way I remember this, para in Spanish is two, so attracted to the magnet. I don't know, that's how I remember it. All right, so we have to indicate the electron configuration for the iron ion. What I do for these problems is write the standard one first, and then I write the one for the ion. So our standard iron configuration would be, so it's a transition metal. So it would be argon 4s2 3d 1 2 3 4 5 6. And so they want us to find the electron configuration for the ion one. Okay, so remember that we take out those electrons from the s orbital first. So we take these out, and that gives us so you might see it like that, or even like without the 4s. No. No. So in this case, answer is C. Does that make sense? Yeah, okay. And also we have to indicate whether it's paramagnetic or diamagnetic. And if we were to draw this, remember that we have 5 d orbitals, so let me just draw 2, 3, 4, 5, pretending that this is the 3D. So remember we have to fill them out like that. 1, 2, 3, 4, 5, 6. And so we have unpaired electrons, and that's paramagnetic then. Good? Okay. We get into periodic trends, and when I took the ACS, there were a lot of conceptual questions based on this. Ionic trends are very important to determine like the behavior of atoms and how we have set trends in the periodic table. So we have several of them actually that we have to understand. Do not just memorize, make sure you understand them, because if you forget on the test, if you memorize them, then there's not a lot you can do. But if you understand them, then you don't even need to like think too hard on them. All right, so let me start with atomic radius. Atomic radius increases from top to bottom because we're adding energy levels each period that we go further down. So atomic radius increases top to bottom, but decreases from left to right. And that's because our effective nuclear charge is increasing from left to right. So let me summarize here. So atomic radius increases top to bottom, decreases left to right. Now, the effective nuclear charge trend is not here, but you have to understand that the atomic radius decreases from left to right because of that reason. So we know that the effective nuclear charge is the shielding effect, so the ability of the core electrons to shield outermost electrons. Remember that the formula is number of protons of like the original atom minus core electrons. So if we were to like calculate it, I don't know how much time I have. Okay. That's not what I wanted to put. So if we were to see, if we were to like do lithium, again, we know that the atomic number is 3. So number is 3. So that means we have 3 protons in our nucleus. And our core electrons are given by the previous noble gas. So in this case, our core electrons is 2. So 2 core electrons. So our effective nuclear charge will be 3 minus 2 equals plus 1. This is for lithium. If we were to do it for beryllium, which is right next to it, we know that beryllium has atomic number of 4, which means it has 4 protons minus same core electrons. That gives us a plus 2 effective nuclear charge for beryllium. That's probably not correctly spelled, but you get the idea. So, yeah. Oh, I hadn't seen it like that. Maybe. I'm not sure. I know that the radius decreases from left to right because of that reason, because the effective nuclear charge increasing. So they're inversely proportional to each other. Yeah. All right. Does everyone understand that? Yeah. So that's a good question. So the core electrons are given by up to the previous noble gas. So make sure, like, if you're unsure, write the electron configuration, and according to the rules, remember, like the p block, d block, s block, you identify core electrons versus valence electrons. Yeah. Does that make sense? Yeah. So our core electrons for sodium would be 10, because our previous noble gas is neon. which has 10 electrons. I'm sorry, what? You sure? Okay. An anion, okay. So, let me see. Good. All right. Let's see. Let's do oxygen. So if we do oxygen, it has an atomic number of 8. So that means it has 8 protons. And then the core electrons are still 2, because our previous gas is helium still, which means that our effective nuclear charge is +6. I'm not sure, like, they're probably related, but I don't want to, like, generalize. Yeah. Maybe. Like, I just think it's, like, important to, like, understand the concept. Yeah. So, everyone good with that? Yeah. All right. Yeah. So, FE would be a little different just because we would have, like, remember that for FE, our valence electrons would be S and D, so N minus 1D, but our core electrons are still up to argon. It's still, for that case, it's 18. Yeah. It's good? Yeah. Right. So you do the core protons minus the core electron. Let me see. Yes. So protons minus core electrons, because we want to see the shielding effect. Yeah? All right. So those are those two. Just understand that they have an inversely proportional relationship. All right, let's do electron affinity and ionization energy since they're related. So electron affinity, remember, is usually a negative value. And it's defined, so electron affinity it's like how much atoms or elements want those electrons, want to gain electrons. And they usually, the value is usually negative because they release energy when they do. So it makes sense that our electron affinity is getting more and more negative, so like increasing from left to right, because what do we have on this side of the table? We have nonmetals. They're the ones that want to gain those electrons. So that makes sense. Does that make sense? Yeah.
So the more negative that number is, that means the more it wants to.
Yeah, the more it wants it, because that means the negative is associated with the energy they release when they gain them. Yeah. Okay. So it makes sense that increases from left to right because we have the nonmetals here, and then the metals want to lose those electrons. They don't want to gain anymore. Ionization energy. So let me finish this one. Electron affinity. How much the elements want the electrons. And so the one that goes along with that, it's ionization energy. Ionization energy is the energy that it takes to remove an electron from an element. Oh, it did have batteries. It's just they said it was too low.
Oh.
Yeah.
Okay.
You want me to take it off?
No, never mind.
Oh, okay. All right. Okay. So ionization energy is the energy associated with removing electrons from an element. Yes, yes. That's why, so ionization energy, the energy associated with removing electrons from an element, so because we have to input energy, it's positive. So make sure you don't confuse those signs. So electron affinity is negative, ionization energy is positive because we're putting energy into what we're doing. Think about it. If you're putting money into your bank account, that's positive. If you're taking out money, it's negative. Kind of thing. All right. So that's why ionization energy increases from left to right, because those nonmetals do not want to give up those electrons. They want more. They don't want those electrons to be taken out of like their shells. Whereas the metals do want to like release those electrons. Does that make sense? Yes, because they pull on them tighter, so it takes more energy to take away from them. It's like taking away candy from like a little kid, harder. Okay, so they're both related by electronegativity, which is not on here. So those electron affinity and ionization energy are related by electronegativity. And we know that fluorine is the most electronegative element. And it's here. So that means our electronegativity increases that way. Let me see if I can find a pen. Okay, does that make sense? And then metallic character versus non-metallic character, this is usually not discussed as much as the other ones, but it's still important to note. Our metallic character is increasing as we're getting closer and closer to our metals. And that makes sense because we're getting closer to the metal, so they behave differently from the non-metals. Oh, also, there's another one that's missing here, I think. Yes. Well, I'll review it when we get there. No, just kidding, we got there. So that's for atomic radius for neutral elements. If we have ions, let me make a little table here. If we have ions, and we have, hello? 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 Hi. Died. Do you have another one, or should I use this one?
Use that one. I'm gonna go get batteries.
All right, thank you. All right, I'm gonna try to talk loud because they're getting new batteries for the other one. So if we have ions, remember that cations are positively charged elements, whereas anions are negatively charged elements. And so cations, because they're positively charged, it means that you lost electrons. Loss of electrons. Anions, you gain electrons. Okay. For cations, since you're losing electrons, but you're keeping the same amount of core protons, then those core protons are pulling those electrons closer into it. So that's why cations are smaller than their parents. Instead, for anions, we still have the same number of protons in the nucleus, but we're adding more electrons, and remember those electrons are repelling each other. So it's going to make our anions bigger than their parents, or larger than their parent. Okay. Does that make sense? That's important in order to solve these kinds of questions. So arrange these atoms and ions in order of increasing radius. So if we look at that, cesium should be our smallest, xenon, yeah, thanks. Xenon should be the second smallest, and then iodide should be the largest one. So for increasing, xenon, so that corresponds to B. Let me check. All right, does that make sense? Yeah.
So do we just ignore like their actual weights of the atoms, and we only pay attention to if it's an anion versus a cation?
That's a good question. No, actually. Look at them on the periodic table. Kind of cheated because I already knew where they were. Okay. So if we look at it, we have cesium here, xenon is here, and then iodide is here. So still, I mean, I guess yes and no, because even if they were neutral, xenon would be smaller than iodide, which is the case. But cesium is another level, energy level, so it should be bigger if it were neutral. But since we remove the electron, it's going to be smaller. Does that make sense?
Can you scoot it over?
Yeah.
Okay, yeah.
You see that? Yeah. Okay. So look at both, let's say. Okay. Yeah. I'm sorry, what? Oh, okay, yes. So these three are isoelectronic, which means that they have the same number of electrons. But even though they have the same number of electrons, they don't turn into the other. They just gain the stability of like the noble gas. Does that make sense? So remember that our metals tend to lose electrons and form cations, and our nonmetals tend to gain electrons and form anions. Yeah. That's a good question. Thanks. All right. And so another thing I wanted to say, they gain or lose electrons to gain the stability of the noble gases. That's why they do it. Yes. Noble gases? Noble gases? That's a good question. No. So in here, the 4s, so let's say calcium, we lose those 2 electrons. So it's like our s orbital would become empty, and then we make it to argon. In the case of, let's say, oxygen, if we gain 2 electrons, we gain the stability of neon, but it's still in the 2p shell. Does that make sense? Yeah? Okay. Good? I don't know why this is here. All right. Shay? Cesium is the smallest because it's a cation. That means it lost an electron, and its cesium ion is smaller than its parent. Does that make sense? All right. With ionization energy, you might get asked a question like this. So since ionization energy is the energy that takes to remove an electron, we see a trend on the periodic table. So, okay. So, our ionization energy increases as we continue removing electrons, because those core protons are pulling on those remaining electrons more tightly. So up until the point that we get to the core electrons, and then in order to remove a core electron, you would see a huge jump in energy because it's super hard to remove. Does that make sense? So in this case, if we look at the trend, we see the first ionization energy 786. For the second one, it increases to 1,580. For the third one, 3,230. For the fourth one, 4,360. But then the fifth one is 16,000. So our jump of energy indicates, let me emphasize huge, indicates that we are trying to remove a core electron. So if we look at like our choices, magnesium couldn't be it because we would have a stable one, a stable second ionization energy, but the third one would be super large. So we can cross that one out. For aluminum, we would see a stable first, second, and third, but our fourth one would be huge. So that's not it. The next one is silicon, which we have a stable first, a stable second ionization energy, a stable third, a stable fourth, but then our fifth is huge. You guys see that? So that's why it's silicon. Yeah? Yeah. It wouldn't be phosphorus because we would have that huge jump on the sixth ionization energy. Does that make sense? Yeah? All right. So for which element is the gaining of an electron the most exothermic? We know that it's most exothermic when we're going towards the nonmetal side. And out of the options, we see that fluorine is there. And automatically, you should know that fluorine is the most electronegative atom, so it's going to be the most exothermic value for gaining that electron. Does that make sense? Yeah. Okay. Now we continue on atom pairs. Hi. Yeah. Cool. So this one's low, and I was using the handheld, and it ran out of batteries.
Okay, yeah, I can turn that up for you.
Thank you. All right. Oh.
No, the number 6. Can you explain it?
Oh, okay. So gaining of an electron. So this is asking us about electron affinity. We know that our electron affinity gets more and more negative as we go towards the nonmetal side, right? More negative. And we know that fluorine is our most electronegative atom, and it's in there, so it will be the most exothermic for fluorine. Yeah, got it. Okay. All right. Choose the number 7. Choose the larger atom from each pair. Again, atomic radii. We have to look at where each of them are. So between aluminum and I think that's indium, maybe. All right. So aluminum is here and indium is here. So we know that our atomic radii increases from top to bottom, so our indium would be the largest atom. So indium between silicone, oh, nice, thanks. Between silicone and nitrogen, so thanks. Yeah. Thank you. Thanks. All right. So between silicone and what was the other one? Nitrogen, thank you. So we have silicone here and nitrogen here. So we know that still top to bottom, silicon would be the larger one. And phosphorus and lead. So we have phosphorus here and lead is here. Again, lead wins. And carbon and fluoride, we have carbon here and fluoride here, and we know that our atomic radii decreases from left to right because of the effective nuclear charge, and so carbon is the largest one. Yes? Number 5? But do you understand it? Do you want me to? Okay, yeah. Okay, so now they're asking us to arrange this isoelectronic series in order of decreasing radius. So straight off the bat, we know that they have the same number of electrons, so we can organize the radii. Organize the radii in terms of whether they're anions or cations. So we know that our cations are smaller, and we have 2 of them. Our magnesium would be smaller because we still have the same number of core protons, and we've lost 2 electrons, so even tighter. I'm doing this backwards. All right, let's start with the anions. So because of the kind of like the same reason, our anions, we have 2. Since we've gained 2 electrons, oxygen is larger than fluorine because like they're pulling each other even further. So then we have fluorine, and then we're going to have our neutral atom because that's still bigger than the cations. And then we have sodium that's only lost 1, and then magnesium that has lost 2. Does that make sense? Okay. All right. So now we have to draw the full orbital diagram for each element. I think I have to start going a little bit faster because we still have more to cover, so if you have any questions, just ask. All right, orbital diagram. So I'm gonna do the shorter one, so we have, so it takes less time. So nitrogen, it's a non-metal, it's 7, number 7, and so the noble gas behind it is helium, and we have our 2s filled, then we have our 2p, and we have 1, 2, 3, 4, 5. 3, 4, 5. Good? Okay. For fluorine, it would still be helium as core, and then we would still have 2s, 2p, but in this case, we have 1, 2, 3, 4, 5, 6, 7. So we have 7. Wait. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, just like that. So, yeah, I think this one has an extra one. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, it's like that. 1, 2, 3, 4, 5. All right. Sorry about that. Then magnesium. Our core electron would be neon. And it's in the third row, so 3s. And that's it. We don't have a 3p yet. And then aluminum. I don't know where I'll fit it. Still neon. We only have one in the p orbitals. You might see them like little lines, you might see them in boxes, you might see them like actually signifying the energy levels. Just know that it's still the same thing. Okay. Which pair of elements is most likely to form an ionic bond? We know that ionic is metal plus non-metal. This is like reviewing, like naming stuff too, which is from Chem 1A. Nitrogen and oxygen are both non-metals, so that's not an option. Carbon and hydrogen, even though hydrogen is on the other side, it's still a non-metal. Sulfur and oxygen, non-metals, so calcium and oxygen is our only choice. So CaO. Does that make sense? Okay. All right, so which set of elements is arranged in order of decreasing electronegativity? So decreasing, so we have oxygen, selenium, no, oxygen, sulfur, As, which is arsenic, and I don't know what that one is, germanium. All right. So oxygen, sulfur, As, and Ge. All right, so our most electronegative should be oxygen because it's closer to fluorine, then sulfur, then arsenic, and then germanium. And that corresponds with option, so with B. So we have ionic bonding versus covalent bonding. Always, like, do not get them confused. Ionic bonding is the transfer of electrons. Covalent is the sharing of them. When you draw fluid structures, know that for ionic, you're going to see brackets. For covalent, they're actually sharing, so you see actual bonds. So the way I remember this is ionic, I don't like to share. That's why ionic doesn't share electrons, it transfers them. Occurs between a metal and non-metal. High melting and boiling points, high polarity. They're usually solid at room temperature, and two things that are relatable to that is lattice energy and Bohr-Haber cycle. Lattice energy is just, well, we'll go into that. Examples include sodium chloride and magnesium chloride. For covalent, we have the sharing of electrons between two or more nonmetals, and we have low melting, low boiling points, low polarity, and they're liquid or gaseous at room temperature. So examples, methane and molecular nitrogen. So I wanted to go into lattice energy because there's like two things that are important here. Well, like everything is important, but lattice energy becomes less exothermic as ionic radius increases. Remember that this is governed by like our charges. So the charge on the cation times charge on the anion divided by the distance. So if our distance between the two, so if our atoms get larger in size, our lattice energy will decrease or become less exothermic, because remember this is still a negative. Because you're increasing here, you're decreasing lattice energy. Also, lattice energy becomes more exothermic as magnitude of ionic charge increases. So if we have +2 and -2, it's going to be, the attraction is going to be larger than for just +1 and -1. Yeah. Remember that lattice energy is just making the solid like an ionic solid. So make ionic solid. All right. We get into Lewis structures. So we get into Lewis structures, count valence electrons for each, determine which atom has to be the central atom. It's usually the one that needs more electrons. So distribute bonds between atoms, then add lone pairs to terminal atoms. So first you start giving electrons to the outer ones, and then the remaining ones you put them on the central atom. That's how you know where to put them. And make sure you know that like some of them may have like incomplete octets or like expanded octets past, I believe, energy level 3. Huh? Yeah. So 3 and down. Expanded. All right. And make sure you like add double bonds and triple bonds as needed, like where you need them. I'm gonna like finish the guide and then come back with maybe like some examples on Lewis structures. Okay. So bond lengths. It's the distance between the nuclei of bonded atoms. Single bond has a larger distance than double bond, and double bond has larger distance than triple bond. Remember that. So length and strength are inversely proportional. That means that the shorter the length that is, the stronger the bond, because those nuclei are like pulling each other even tighter, so it's going to be harder to split them. Single bond is sigma, double bond is sigma and a pi, and triple bond is sigma and 2 pi. Okay. Polarity means that one atom has a stronger pull on the other electrons than the other atom. Differences in electronegativities determine polarity. So highly electronegative atoms are like bullies. They want those electrons, so they're pulling them tighter than the other ones. So for nonpolar, like there's a range. Let me just write them. So form when difference in .0 and 0.4, and we have equal sharing of electrons. and we have examples. So like our diatomic molecules will always be covalent or nonpolar, and then carbon and hydrogen, it's really low, so they're still considered nonpolar. For polars, we have when the difference in electronegativity is 0.5, 1.9. So here we start seeing like partial charge, like how one element is like slightly positive and the other one slightly negative. So I'm about to write that. Partial charges. And there's unequal sharing of electrons. Examples of that include like hydrogen chloride, because chloride is more electronegative than hydrogen, so it's pulling those electrons closer to it. Ionic, so formed when electronegativity is more or equal than 1.9, well, not equal, more than 1.9, and electron is transferred from cation to anion. So ionic, you don't even like have to calculate it. If it's a metal plus non-metal, that's an ionic bond. So they don't even share, they like transfer electrons. So sodium chloride is an example of that. Okay. It's important to know that even though a molecule may have polar bonds, it may still be nonpolar, because two conditions must be true for a molecule to be polar. First one, there must be at least one polar bond or one lone pair of electrons present, like in the case of ammonia where nitrogen has lone pairs. And number two, the polar bonds, if there are more than one and lone pairs, must be arranged so that their dipole moments do not cancel each other. So in this case, it's polar because fluorine is super electronegative, so it's pulling those electrons closer to it. But let's look at, for example, water. We have like the structure is bent. So, or I don't know if we go into this. Yes, we do. So let's just do it. Electronic geometry is tetrahedral. And then molecular geometry is bent. And we have dipoles because the oxygen is pulling those electrons. So we have individual dipoles that generate a net dipole since they don't cancel each other. And so this will have a slightly positive charge, and this will have oxygen will have a slightly negative charge. However, in the case of carbon dioxide, we do have dipoles, individual dipoles, because those electrons are more attracted to oxygen than they are to carbon. 2, 4, 6. 2, 4, 6, 8. However, since they're pulling each other on the same direction, like opposite but same magnitude, opposite directions, they're canceling each other out. So we don't have a net dipole. Does that make sense? All right. So hybridization is like how orbitals combine to form molecules. Let me just do the hybridization for carbon. So if we look at CH4, and we look at carbon specifically, so we know that it's going to be 1s2, 2s2, and then 2p um, 4. Okay. Wrong. Sorry. All right. So, according to this, carbon only has 2 available electrons to mix or like to combine with other elements. And we know that carbon is supposed to share 4, right? So what must happen is hybridization, where we hybridize the s and p orbitals. So we move one there and we raise that level. So our hybridize is going to be so now we have 4 available electrons to combine with those hydrogens. And the orbitals that are given by those hydrogens are 1s. So that's why we have that here sp3 is, that carbon is sp3 here. Does that make sense? Okay. We go into valence shell repulsion theory. So this is getting into electronic geometry. Touched a little bit on that here. Electronic versus molecular. We know that regions of high electron density around central atom are arranged as far apart as possible to minimize repulsions. Lone pairs of electrons require more volume than shared pairs, and they're like pushing each other like as much as they can. Lone pair to lone pair is the strongest repulsion. Lone pair to bonded pair is like in between, and then bonded pair to bonded pair is the weakest repulsion. So you have to like know what shape it will make when molecules are formed. Just make sure you understand and know for sure that our electronic geometry never changes when we have lone pairs. Never changes with lone pairs. What changes is our molecular geometry. Which is the shape. So in this case, if we have 4 regions of electron density around a central atom, our electronic geometry will be tetrahedral. If we start having lone electrons, so if we have 1 lone pair, we're going to become trigonal pyramidal. If we have 2 lone pairs, we have bent. But even so, like these 2 still have the same electronic geometry, which is tetrahedral. Does that make sense? Like that's like really important to note. All right. And depending on how like the lone pairs distribution or the bonded pairs, you're going to have different angles. Yeah. All right. Here's a color picture. Also know the hybridization. So in this case, so we have SP, SP2, SP3, SP3D for hybridization around the central atom, and then SP3D2. You just like keep adding orbitals depending on the electron regions that you have. Yeah, since we have only one s orbital, then we only have 1. We have 3 p orbitals, then we have 3, and then d goes up to 5, but we usually cut it off at 2. Another thing to keep in mind, all these, this first column, are going to be nonpolar. Non-polar. Because the dipoles cancel out. Huh? Yeah, so like the first column of like this. All right, so if we were to state the hybridization and shape for each of the non-hydrogen atoms, so here we have 1, 2, 3 density regions. We don't count the double bonds, like we only count them as one, so sp2. Same for this one, sp2, 1, 2, 1, 2, 3, sp2, 1, 2, 3, sp2, 1, 2, 3, sp2. This one's sp3 because we have 1, 2, 3, and 4 electron density regions. For oxygen, keep in mind that you still have lone pairs despite the fact that they're not drawn, so it's still sp3, 2, 4, 6. We have one here, 1, 2, 3, 4. So it's still sp3, and then same for here. Now for sigma bonds, remember that single bonds are 1, and then when we start having double and triple bonds are what? So we still have one sigma bond, and then we have pi bonds. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So that's what I got. Make sure to like check it. Sigma bonds. It's 24? Okay, thanks. All right. 24 sigma bonds, and then how many pi bonds do we have? Three, 4? It's 4. Because we have 1, 2, 3, 1, 2, 3, 4. Yes, 4 pi bonds. All right. I won't go like too into detail about like hydrocarbons. I just wanted to like mention that for alkanes, our formula is CnH2n plus 2. Alkenes and cycloalkanes is CnH2n, and alkynes are CnH2n minus 2. So other than that, they follow like pretty similar rules. They follow pretty similar rules where you want to like give the lowest priority to the substituents, and as soon as you start having double bonds and triple bonds, you want to give those the priority. It's also like you have to know like your substituents, so it's methyl, ethyl, propyl, as soon as you're adding like carbon chains. And here we have, they start counting to give the double bond the highest priority, so they count 1, 2, 3, 4, 5, and so 2, we have a methyl here, and 2 methyls here, so 2,5,5 trimethyl 2-hexene. Because our parent chain has 1, 2, 3, 4, 5, 6 carbons. Yeah? So if we have a chance, I'll go back to this, but like there's so much to cover. But this is really easy. Don't like get freaked out. It's just practice. Yeah. I'm not sure. I really don't know like whether you would have to know how to draw these. Usually when they give you the name, it's easier to draw it like this and then like see it. I don't know, it's easier to visualize, but it's up to you. You should know that the peaks at the ends are like CH3s, and then that you still have hydrogens. So not because you only have 2 bonds here, that carbon still has 2 hydrogens to complete its octet, but we don't write them. Yeah, so keep that in mind. Okay, so bonding order, number of electrons in bonding, molecular orbitals minus number of electrons in anti-bonding molecular orbitals divided by 2. You should be able to fill out this diagram. It's a little bit simpler for like our lightest elements. But we use this one for bromine, carbon, and nitrogen, and this one for oxygen and fluorine. So draw the molecular diagram of C minus 2. Let me see if we have time. Yeah, I think we do. All right. So if we're doing the molecular orbital for carbon 2 minus 2, we're going to use this one. So (2s). Let me draw it lower. I don't think we'll get that far, so I'll just leave it here. And then we have our p orbitals. All right, and so these are like connected, as you know. Okay. So the way this works is the center is going to be our molecular orbital, and the sides are going to be our atomic orbitals. Since we're doing carbon, that means each carbon has a -1 charge because of the gain electron. So we know that carbon has valence electrons of 4, so but we gain 1, so 1, 2, 3, 4, 5. Same for this side, 1, 2, 3, 4, 5. And then we just start putting them depending on the orbitals. So we have a total of 10. So the addition of these two should equal what we have in the center. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes? And so we have 10 in here and 5 and 5 on both sides. And so if we remember that the ones with the asterisk are the anti-bonding, so they're higher in energy. And these are bondings. And so if we were to do the bond order, we would see that bonding are 2, 4, 6, 8. And our anti-bonding is just 2 divided by 2. That gives us 3. So the bonding order for this would just be 3. Yeah. So in this case, it's not paramagnetic because all our electrons are paired for the molecular orbital. But yeah, he can ask from this. So make sure to be able to recognize it. Does that make sense though? So remember that the higher the bonding order, the more likely we are to see them in nature because it's more stable. So if you have a really low bonding order, then it's unlikely, like it's likely that it's unstable. Usually like related to like some noble gases. All right. Now we get into gases, which is our last chapter. Pressure, ATM is standard unit, usually 1 ATM, which equals 760 millimeters of mercury. Yeah, thank you. Same in torrs. Temperature, standard unit of Kelvin is whatever we are giving in Celsius plus 273. Do not forget this. Do not forget, usually they give temperature in Celsius. So if you plug it into PV, nRT like that, it's going to be wrong. So make sure you are working with the right units. Density, mass, or volume. We can find mass from using PV, nRT to find moles and converting. So the N in that formula is really helpful because we can find like moles, molar mass, and density from it. So remember that. So if you feel like you don't have enough information to work it out, it's usually because of that. We'll get to work on one in a few seconds. Standard temperature and pressure. Temperature is 273 and pressure is 1 atm. So we get into the loss. From the loss is not just plugging it in. I feel like it's more important to understand the reasoning behind it. So how the variables change regarding like how you change one another. So for boils, the pressure of the gas is inversely proportional to its volume. And this makes sense. So our formula is PV equals PV. This makes sense because if you have a container, if you have two containers, just kidding, you just have one for now. And you're pushing, you're inputting pressure into that. There's some molecules here. You have a great volume and normal pressure. But if you increase pressure, you decrease the volume of those particles, and now they're closer together. Does that make sense? So as we increase pressure, we decrease volume. This is the same case of like when you're breathing. If you breathe in, your lungs expand, so you're increasing volume, you're decreasing pressure. And backwards, the other way around. Char's law, volume is directly proportional to temperature, and I know you guys had a question on that on the test. So if volume increases, temperature also increases, and the other way around. Avogadro's, volume is directly proportional to the number of particles. So if we increase moles, we increase moles, we increase volume because they occupy more space. It's important to note here too that if at constant temperature, if we increase, so heavier molecules are going to travel slower. Remember that too, because I would say for like the ACS, be able to like put things into graphs and pictures because they like that. At least I remember that. So be able to like recognize because that's the way they test whether you understand it. So make sure that you're able to like recognize diagrams such as this, diagrams relating like weight and speed and things like that for all the conditions. Standard conditions, we already said that. Mole fraction, so we get this from Dalton's law of partial pressure. And it is useful because he says that the total pressure is equal to the pressure of A, pressure of B, and so on. And from there, we can calculate the mole fraction that corresponds to that. So if we want to find out the pressure of gas A, we just need to multiply the mole fraction of A, which is the ratio of that gas to the total, times the total pressure. So that's what we see here, and one of the problems at the end plays with that. Okay, there we have it. If we're collecting gases via water displacement, they're like the values are known. Usually, they're given to you. In order to find the gas, you subtract the partial pressure of water vapor from total pressure to find collected gas pressure. Molecular velocities of gases, use root mean squared method to find average velocity of a sample, and it's equal to your root mean squared equals square root of 3 times r times t over molar mass. And so real gases, so in real life, so the kinetic molecular theory is meant for ideal gases. But in reality, not all gases are always ideal, especially at low temperatures where like our intermolecular interactions do have an effect on how these particles behave. So usually at low temperatures, we have lower pressures than predicted. So in real life, intermolecular interactions occur, and these interactions are not like completely elastic. So there's a loss of like some energy when they do that, usually. Volume of particles actually has an impact, and so for real gases, we have an adjustment of the P, the usual PV nRT, and that's why we have adaptations to account for those intermolecular forces. There's no, like, you don't need to, at least for Dr. Ditson, you don't need to memorize this, but like understand why we have it. That's the main reason why. Diffusion versus effusion. So the effusion is just the gas traveling from higher concentrations to lower concentrations. And then effusion is the escape through a hole. Let me give you like the technical definition. If I can find it. Okay, yeah. Collection of molecules escaping through a tiny hole in a vacuum. So the fusion would be something like when you buy like helium balloons, they over time deflate because they're traveling from high concentrations to low concentrations, which is outside. But for a fusion, it would be like the equivalent of you like piercing that balloon and it's all escaping through that little hole. Yeah, okay. They may have like diagrams for that. Just make sure you understand that too. Okay, so what volume of O2 measure at 17.7 degrees Celsius and 0.978 ATM reacts with 15.1 to produce carbon dioxide and water. So they give us the formula, and we're given this, and we want to find related to that. So we have to convert. We have to find the relationship. So I believe the weight is 58. We have to convert that to moles. So this is useful for like reviewing stoichiometry too. And so now we have to see the relationship between C4H10 and O2, so we know how many moles we have for O2. So 2 moles C4H10 react with 3 mole O2, and I get 1.69 mole O2. We did that because we want to know specifically volume of O2. So it helps it helps for you to write out what it's given and what you need to visualize it. Now we can plug it into PV equals nRT. Pressure, they told us that it was, not 1 atm, just kidding. 0.978 atm times the volume. Oh, that's what we're trying to find. Just kidding. Equals the moles of oxygen, 1.69 moles of O2. Our gas constant, which is 0.0821. I don't remember the units, but. And then the temperature, they gave it to us in Celsius. So you need to change that to, let me put a little. So 17.7 plus 273, that's 290.9. So that's what we plug in here. And for volume, then I got 41.27 liters. Does that make sense? Yeah. Okay. They always give you the information that you need, so don't freak out. Just write it out. You're probably gonna see it eventually. All right. So, I broke down. Last two. Calculate the density of krypton at 308 kelvins and 0.69 atm. So from our PV nRT, remember we said we can find density. And so the adaptation to find density would be PM, there we go, over RT. Thank you, Skyen. All right. Let me see. Where is it? Okay, here it is. But you can choose to solve it like find moles and then N, which is moles. If you want to solve it step by step, that's fine too. Molar mass equals grams over moles. So if you want to find number of moles first and then find the molar mass to find volume, then that's fine too. But this is like a combined formula to find density. So if we plug in, we have pressure at 0.693 atm times molar mass, which is 83.80 grams, over R, and the temperature, which is 308 Kelvin. And we have 2.30 grams per liter. All right, last one. So a sample of oxygen was collected by displacement of water at 25 degrees Celsius. The atmospheric pressure was 700 torrs. What is the mole fraction of O2? Vapor pressure of water is 24 torrs at 25 degrees Celsius. So since we know that our P total will be equal to P of water plus, what are we? Oxygen? P of oxygen. We can find the mole ratio for oxygen based on the partial pressure. So we have, total pressure is 7 torr. The one for water is 24 torrs. So we're missing partial pressure of oxygen. Partial pressure of oxygen is then 676 torr. And so remember that from Dalton's partial pressure, we know that we can find partial pressure of oxygen is equal to the mole ratio of oxygen times P total. So using that, we can find our mole ratio of oxygen by doing PO over PT, which is equal to 676 torrs over PT, which is 700. So the ratio of the oxygen gas in regards to the total pressure. The pressure of the oxygen gas in relations to the pressure of the total gas. And that gives us 0.966 torr. And you may like change that. You may be asked to convert that to ATM. Oh, sorry, that's a ratio. Never mind. So no conversion needed. All right. Yeah. All right. Good. Well, I hope this was helpful. I know I didn't get it. Yeah.
Can you go back to the one where you're doing the AO and
Yeah.
you're doing on the molecular?
Oh, yeah, sure. I can't find it. Let me see. Backside. Oh, here it is. Okay.
Can you walk through this again?
Yeah.
Okay.
So, can you see that far? Okay. So we're trying to write or draw the molecular orbital for carbon for this. But it's gained 2 electrons, right? Okay, so we know that we have to use this orbital because of the other slide. You get that, right? Okay. So our molecular orbital is going to be in the center, and then each side is the atomic orbitals. So how they like bond together. So since our molecule is C2 with a -2 charge, we know that each carbon gains 1 electron. So usually our neutral carbon has 4 valence electrons, but since we gain 1 more, now we have 5 valence electrons. So that's how you fill them out here. So our valence is 2s and then 2p here. So we're going to fill out so imagine you're doing the atomic orbital first, like the regular electronic configuration. So you start 2s and then 2p. So we have 1, 2, 3, 4, 5. Same on the other side, 1, 2, 3, 4, 5. And then we start, we just fill out the molecular orbital diagram, where we just start, putting them from lower energy levels to higher energy levels. So added together, we have 10. So that's the same number we should have in the center. So we are doing 2, 4, 6, 8, 10. We're literally filling up from lowest to highest. And then from that, we can see different things like paramagnetism, diamagnetism. We can calculate the bond order, and that tells us about the stability of the molecule. In this case, the ones that have asterisks on them are anti-bonding, and the ones that don't have it, the ones that are bonding, don't have it. So our bond order is 8 - 2. So the 8 is corresponding to the bonded atoms, bonded electrons. And we have 1, 2, 3, 4, 5, 6, 7, 8. The anti-bonding is just 2 from here. And then divided by 2 is 3.
Will it always be 2 anti-bonding?
No. So
Are these supremacist? Is that the mass of the
So that varies with the molecule you're drawing, because you may start filling, so depending on the number of electrons that you have, you may get to this part. And so this is anti-bonding. So you would add that to your anti-bonding count. That's a good question. All right. Is that good? Okay. Well, I hope that was helpful, guys. Good luck on your test tomorrow. I might proctor it, so you might see me tomorrow again.